The synergetic air-breathing rocket engine, or SABRE engine, can be thought of as an extension of the liquid air cycle engine, or LACE engine. This project gained momentum in the 1960s as part of the US Air Force's effort to create a successful spaceplane. Other examples of attempted spaceplanes are the X-15, the Space Shuttle, the Soviet Buran, and more recently the X-37. However, the latter three are the only spaceplanes to ever reach orbit. This task involved expending large booster stages, SRBs, and fuel tanks. Rocket propulsion is based on the principle of conservation of momentum. It works by ejecting hot gas from the nozzle of the engine at high velocity, which exerts a force on the rocket in the opposite direction. To achieve high exhaust velocity, fuel is combined with an oxidizer in the combustion chamber, which causes rapid expansion and forces the exhaust to accelerate down through the nozzle.
As mentioned, all combustion processes need a fuel and an oxidizer. In the case of the SABRE engine, hydrogen and oxygen are used respectively. In reality, the rate at which combustion takes place in a rocket engine is so rapid that it's difficult to keep the fuel flowing at the same rate. In the SABRE engine, pumps are used to compress the fuel and oxidizer and feed them to the combustion chamber at high densities. Pre-burning is part of the combustion process in rocket engines. A small proportion of the propellant is routed to the pre-burner where it is ignited. The heat produced from the pre-burner is used to power the turbines and compressors involved in the combustion process. The main difficulty with using most liquid oxidizers is that cryogenic propellants must be stored at very low temperatures. For example, the liquid oxygen used by the Merlin 1D engine of the SpaceX's Falcon 9 rocket must be stored at minus 183 degrees Celsius. On top of this, eliminating the need to carry an oxidizer for use during the atmospheric stage of flight greatly reduces the required oxidizer tank volume, therefore allowing for increased fuel volume. For the SABRE engine, a combined cycle rocket engine with two operating modes is adopted. At low altitudes, the inlet cone remains open, allowing air to enter the engine and pass through the turbo compressor and an air pre-cooler. It is then fed into the combustion chamber of the rocket engine, where it is ignited with liquid hydrogen propellant, which is stored in onboard tanks. At a speed of Mach 5.14 and an altitude of 28.5 kilometers, the inlet cone closes and the flow of oxygen is replaced by liquid oxygen, which is stored on board.
The SABRE engine works on two stages. Stage 1 happens below Mach 5.14 and altitude 28.5 kilometers, and this is the air breathing mode, and it consists of a simple translating axisymmetric shock cone inlet in front of the engine, which slows down the sucked environmental air to subsonic speeds by means of two shock rarefactions. Some part of the sucked hot air passes radically through a pre-cooler into the center core, and after the pre-cooler, a turbo compressor is implemented and operates on the same helium loop and Brayton cycle that compresses the air and leads it into the combustion chamber. The general concept of stage 1 is that air cooler brings intake air to cryogenic temperatures, allowing it to be used as an oxidizer. So air is cooled, compressed, then combusted, and it all happens on board.
The helium loop. The helium loop is one of the most important cycles in the SABRE engine, and it is responsible for making the concept work. In other words, it is responsible for cooling hot air entering the SABRE engine and powering subsystems within the engine. A very basic schematic of the helium loop can be seen on screen. The loop starts at the pre-cooler. Cold helium is passed through the pre-cooler where a heat exchange process takes place. Here, the helium absorbs heat energy from the air, cooling the temperature of the air to around 140 kelvins. Following this, the helium is routed through a heat exchanger with hot engine exhaust from the pre-burner. This process raises the heat of the helium to a constant value of 1180 kelvins. The hot helium can then be used to power the turbo compressor to further compress incoming air. In this process, the helium loses some of its heat energy. Finally, the helium can be passed through another heat exchanger with liquid hydrogen. This cools helium to its original temperature, where it can repeat the cycle.
Moving on to stage 2, which happens above Mach 5.13 and altitude of 28.5 kilometers. This is the rocket mode, where oxygen is used as an oxidizer and fed to the combustion chamber. And one key note here is that using air as an oxidizer is not as effective as liquid oxygen, due to the fact that all of the air supplied to the combustion chamber of the engine, only 21% of that is oxygen. Another way of saying this is that 79% of the gas supplied to combustion chamber is inert and does not serve to accelerate the spacecraft.
Specific impulse is the ratio of the total impulse to the weight of propellant used, where total impulse can be thought of as the total thrust output over a specific time interval. Primarily, in rockets, the majority of the mass comes from the propellant, and it is therefore useful to have a metric to compare them against each other. Comparing specific impulses will give us an idea of which fuel is best suited for a certain application. It will also give us an idea of the performance of the engine compared to other rocket engines. In the SABRE engine, a mixture of hydrogen and oxygen is used. When the SABRE engine is air-breathing, it has a specific impulse of 3,500 seconds. In a vacuum, it has a specific impulse of 460 seconds. The efficiency of the SABRE engine cycle has been increased in many different ways. The efficiency of the rocket engine has been increased by adding a series of ramjets arranged in a ring around the main nozzle. Simply put, these ramjets make use of surplus air that passes through the intake but does not enter the combustion chamber of the rocket engine. This effectively turns this excess air into additional thrust, which would otherwise have increased the effective drag that would result from this air passing through the engine.
SABRE engines were evaluated and optimised for efficiency. For the engine, a component level model was developed and energy efficiency analysis was carried out based on said model. According to the results, SABRE cycle efficiency varies from around 30% to around 42% along the flight trajectory, and most of the wasted energy comes from unburnt hydrogen in the exit gas. Potential to achieve SSTO capability. The elimination of the need to carry an oxidizer for burning in the portion of the flight within the atmosphere allows for potentially a new class of spacecraft which has never been achieved before. This is the potential to unlock single stage to orbit capabilities. This is unlike rockets seen in the Apollo or Space Shuttle programs. These rockets underwent staging, which is the act of separating the spacecraft into two or more sections to eliminate dead mass. The sections that were staged were typically left to burn up in the atmosphere until recent advancements have allowed for the recovery of these stages. Cons of the SABRE engine. So one of the intentions of the SABRE engine is to propel people around Earth in short periods of time. However, travelling at such high speeds creates large amounts of friction between the vehicle and the surrounding air. The fuel required to overcome this would make the flight unaffordable and not environmentally friendly. In this day and age, it's just not commercially viable, and the Concorde was discontinued for similar reasons. Although the specific impulse of the SABRE engine is much higher when in air-breathing mode, the vehicle must have a low, flat trajectory compared to that of a traditional rocket. This means that the vehicle will spend much more time in the atmosphere. This increases the heating effect on the craft, and therefore more thermal insulation is needed, which adds weight. Air-breathing craft will also have to incorporate wings for the air-breathing part of the journey. This will increase the drag effect on the craft and reduce fuel efficiency. Although in theory the SABRE engine can be used to propel vehicles to space and return them in one piece, due to the reasons mentioned, it is currently cheaper to just send rockets to space with liquid oxygen tanks and return them to Earth, similar to what SpaceX is doing.
The SABRE rocket engine and its predecessors have been under development at reaction engines for around 30 years now, and it seems that they're getting ever closer to making the rocket engine a reality. As a result of additional funding, real-world testing of the rocket engine and its components has begun in the last couple of years. In 2019, the engine's pre-cooler heat exchanger was tested. Further testing of rocket engine components and the hydrogen pre-burner were undertaken in 2020 and 2021. The pre-burner provides the heat energy to the rocket engine cycle during the initial stages of the flight, and during its testing it was shown that its heat output could be precisely controlled to ensure even temperature to the heat exchanger that connects the pre-burner to the combustion gas and helium. Despite this, it seems that the rocket engine is still a long way away in terms of being a fully operational system. However, with the recent success of these tests, the proof of concept of the SABRE rocket engine has been shown to work, and it can only be a matter of time before it becomes a reality.